We usually think about motion as, well, a push or a pull, right? But what if that whole idea is just wrong? Albert Einstein gave us a totally different and frankly much cooler picture of how things really move, not just here, but everywhere. Today, we're going to dig into the true nature of motion.
All right, so let's kick things off with a classic brain teaser. You've got an astronaut circling the Earth, totally weightless. We say they're floating up there. But are they? Or are they actually in a constant state of falling? The answer to that question completely flips our understanding of gravity on its head. And it all boils down to this one beautiful idea, the geodesic. So to really wrap our heads around this, we've got to totally rethink the most familiar force in the universe. For hundreds of years, we had one picture of gravity, but then Einstein came along and asked us to see it not as a force, but as the actual shape of reality itself. Okay, so what you're seeing here is a huge deal. It's this massive shift in thinking. Newton's idea, which we all learn, is that gravity is some kind of invisible rope pulling things together. But Einstein's general relativity says nope, there's no rope. Instead, something massive like the sun literally creates a dent in the fabric of spacetime, kind of like a bowling ball on a trampoline. So the Earth isn't getting yanked by some invisible rope. It's just rolling along the groove that the sun creates. So if everything is just cruising along these curves in spacetime, how does it decide which way to go, right? Well, it turns out things in nature like to be efficient. They take the straightest line they possibly can. And that path, that's what we call a geodesic. Now, out in the middle of empty, flat space, a geodesic is exactly what you'd think, a perfectly straight line. But in the warped spacetime around a planet, that straightest possible path ends up looking like a curve to us. It's the path anything takes when it's just coasting, with no other forces messing with it. And, this quote from Hartl's book just hits the nail on the head. A free particle, whether it's our astronaut, a planet, or even a beam of light, isn't being forced to do anything. It's just reading the local map of spacetime and following the directions. It's going as straight as it can through a world that isn't flat.
So how does the universe define straightest? Honestly, you can think of it like cosmic laziness. Objects just follow the path of least resistance. And in relativity, that path happens to be the one where, if you were carrying a stopwatch, the most time would tick by. Sounds weird, right? But that's how the universe sees efficiency. It's called maximizing proper time.
This is a perfect way to picture it. If you want to fly from New York to Tokyo, you don't fly in a straight line on a flat map. The shortest, most fuel-efficient route, the geodesic, is actually a big arc that goes way up north. From our flat map perspective, it looks curved, but for the airplane, it's the straightest shot possible. The universe works the exact same way.
Okay, so we've got the concept, but how does this turn into, the actual rules of motion? If everything just follows these geodesic paths, how do we actually write down the universe's instruction manual?
All right, let's start simple. Super simple. Let's imagine we're in deep space, miles from anything. Space-time is totally flat. The rule for a straight line here is about as basic as it gets.
And here's the rule. All this math really says is that acceleration is 0. That's it. In other words, if something's moving, it keeps moving in a straight line. If it's still, it stays still. It's pretty much Newton's first law, just in the language of relativity. Easy peasy.
But here's the thing. Our universe isn't some empty, flat void, is it? It's full of stuff, stars, planets, galaxies, that all bend and warp space-time. So we're going to need a much more powerful rule to handle that. A master equation.
And this is it. The geodesic equation. Yeah, it looks like a beast, I get it. But trust me, this is one of the most beautiful and powerful ideas in all of physics. This is the universe's rulebook. It tells an apple how to fall, the Earth how to orbit, and light from a distant star how to bend around a galaxy. It's all in there. So let's break this monster down. The whole secret sauce is in that big gamma symbol, the one that looks like a capital T. You can just think of it as the curvature knob. It holds all the information about how space-time is being bent. Now, if you're in empty space, there's no mass, so there's no curvature. You turn that gamma knob down to 0 and poof, the whole complicated mess just melts away, and we're left with that simple straight-line rule from before. The simple case was hiding inside the master equation all along.
Right, so we've got this awesome, but let's be honest, complicated equation. So how on earth do physicists actually use it to predict something like the orbit of a new satellite? Well, they use some really clever shortcuts.
Well, the trick is to look for symmetries. For example, the space-time around a perfectly round star is the same in every direction. And whenever you find a symmetry in nature, it gives you a powerful gift, a conservation law. In this case, it means angular momentum is conserved. Finding these conserved quantities are like finding cheat codes that make solving the whole geodesic puzzle way, way easier.
And get this shows you just how ridiculously powerful these rules are. Using these exact principles, physicists can actually map out the specific path, the geodesic, for something as wild as taking a trip through a wormhole. It's a totally sci-fi idea, but the math gives us a clear rulebook for what that trip would actually look like. Okay, so we've been talking about planets and astronauts, things with mass. But it's not just them. The fastest thing in the universe, light itself, also has to play by the rules of geometry.
See, light always takes the straightest possible path, too. It follows what's called a null geodesic. And if that path goes near a massive object where space-time is curved, then the path of light has to curve too. This is that amazing effect called gravitational lensing, where a huge galaxy can literally act like a cosmic magnifying glass, bending the light from things hiding behind it.
And check this out. The equation for light, it's got the same bones as the other one, right? You still got the acceleration part on the left, and on the right, you've still got those gamma terms, the curvature knobs telling it where to go. The principle is exactly the same. Everything, and I mean everything, just follows the curves of space-time.
And all of this, every bit of it, brings us right back to where we started, with our astronaut. Now that we understand geodesics, we can finally crack the puzzle of whether they are floating or falling.
And listen, this isn't just some abstract theory on a blackboard. We actually build machines to be perfect geodesic followers. These drag-free satellites have a little cube of metal inside that's totally shielded from everything except gravity. The satellite then uses tiny little jets to perfectly follow that free-falling cube. These things are so incredibly sensitive they can actually detect the tiny ripples in space-time itself, gravitational waves.
So here's the payoff. This is the key. What is our astronaut actually feeling? Well, because they are on a geodesic, they are in a freely falling frame. What that means is, in their little bubble of space, space-time feels perfectly flat. All the weird effects of gravity just disappear. They don't feel any force, they don't feel any acceleration, they feel completely and totally weightless. So, what's the verdict? Are they floating or are they falling? The answer is yes, they're floating because they're falling, perfectly in sync with the geometry of the universe. I mean, this just changes everything, doesn't it? Motion isn't about forces and poles, it's about everything just taking the path of least resistance through this incredibly dynamic, curved reality. It suggests that the universe, at its very core, runs on a principle of deep and profound efficiency. So it leaves you with this incredible thought. If the laws of motion are this elegant, what other amazing secrets is the universe just waiting for us to discover?